of chapter 6 by mentioning the three laws of thermodynamics, because there are many statements of them, but first law is essentially the energy balance. Okay, one formulation of the first law is the energy balance we have been working with the entire time. Which is basically conservation. Second law is essentially that entropy generation is always greater or equal to 0 and will be 0 only for equilibrium or reversible processes. Okay, who knows the formulation of the third law? This is from you, right?
You have a perfect crystal
Okay.
at 0 Kelvin's entropy equals 0.
Okay. That's one formulation. Very good, Josh. So one formulation is the one that Josh said, and not every substance at 0 Kelvin is a crystal. If you have a helium, it would be perfect liquid, right? So what Josh has said is that the entropy of all substances in the perfect crystalline absolute perfection for solids or perfect liquid state e.g. for helium is 0 at 0 Kelvin. So at 0 Kelvin, perfect crystal would have 0 entropy. And can we have absolute perfection? No. So an alternative statement is that it is impossible to obtain 0 Kelvin. So alternative okay. So with that ends the review material so far. That was up to chapter 6. I spent 4 weeks, but I would say about 1.5 weeks of that was on unison. So spending 2 weeks or so is not, I think, unreasonable, given that we'll be using a lot of the equations we got. So now we're starting chapter 7, and the first thing is criteria for equilibrium and phase equilibria. So I'll erase this. Before I erase, again, I have to move my office hours half an hour earlier, and they will end sharply at 3:30. 3:30 I'm out the door, guys. And I'm reminding you that I will do a solution of the old exam I have posted Thursday, starting at 3:30. Not in this classroom, although we can pay a visit, but often student organizations have this classroom and say, oh, well, I know 237, nobody else will be there. So yeah, let's just say it will be in 237. It has 48 chairs, about 50 of us, so you may have to hold a couple of chairs from the corridor from the All right. So, new topic, criteria for equilibrium. So, for a closed system, and you should always consider that the fluid moving with bulk flow is a closed system. Okay? For a closed system, the energy balance becomes du dt equals q dot minus p dv dt. We can achieve the thermodynamic states without shaft work, having PdV work as the work involved. Okay, so the work involved is all PdV work. So that's the result of the energy balance. Okay, so no flows in or out, energy, no shaft work, PdV work. Okay. And the entropy balance would be ds dt equals q dot over t plus the generation. And we have the second law that I just mentioned, that S dot gen is always non-negative. Let's consider several cases and see what is the conclusion of those equations. Yes?
How come you don't have like in or out terms?
Closed system?
For, yeah, open. And then just close one.
Yes, this is for closed system. All right. So cases. Now consider several cases. The first one, let's consider we have an adiabatic constant volume system. So, if we look at 711, adiabatic, this goes away, constant volume, this goes away. So du dt is 0, which means u equals constant. Entropy balance, adiabatic goes away. So we have so that tells us that what we have at equilibrium. At equilibrium, don't change with time. That means time derivatives are 0. That means really at equilibrium, ds must be 0. So ds must be flat at the point of equilibrium, yet the only allowable change in ds is to have increase. Okay? Entropy can only increase. What does that mean? That means that this equilibrium state has to be a maximum. since I can only move in direction of increasing entropy, it has to be a maximum. Okay. So conclusion is S must be a maximum, which means the second variation in entropy must always be less than 0. Case 2. Let's consider now isothermal constant point. The first equation now is no longer adiabatic, so Q dot exists. But it's constant volume, so this goes away. So the first equation becomes du dt equals Q dot. And the second equation, this exists. So we have and now substitute Q dot from the first equation.
Dr. Serrano,
Yes.
even if it's isothermal, du equals 0,
Say again?
would that be du equals 0 for isothermal? No?
Isothermal is constant temperature, doesn't mean du equals 0.
But isn't du equals Cv times dt?
That's for
Cool. Plus you have other terms, etc. Pressure. We haven't fixed two thermodynamic variables. Yeah, question?
I have a backtracking a little bit, sorry, but S must be a max. I don't understand that. It's greater than 0. Well, it
Okay.
is 0 there. I know what you mean by that.
At equilibrium, it has to be a flat line.
Okay.
But we can only move in increasing entropy. So if we can only move towards equilibrium in increasing entropy, we can only move this way or this way. So it has to be a maximum.
Okay.
And what does it mean, a maximum? It means that the second derivative, the slope, continually decreases from highly positive, so the second derivative is negative. Yes, Josh?
What's that second derivative with respect to it? Just
It's second differential, respect to anything. Second differential. Whatever is varying, okay, we can only approach equilibrium with increasing entropy.
For an adiabatic, for the cases 1 where it's adiabatic, you have U is equal to constant, and
Yeah.
that's because Q goes to 0. and
Q
then-
dot is 0, adiabatic, dV is 0,
Yeah.
constant volume, so you get du dt equals 0.
Oh, okay.
So the derivative is 0, U has to be
same as
constant.
Okay.
Anybody else? All right, let's continue. So we can plug Q dot in there, and we get ds dt equals 1 over t du dt plus s dot gen. Now, du is right, and somewhere should have so ds, well, actually, let's see how I want to do it. So this is constant volume. So this goes away. So du is the just the right thing. Okay, we're okay here. And
Yeah, just keep.
let me just
The ISO thing.
let me work with
That's
this.
to keep the gas from system to another system. Because
Multiply the whole thing by t. So t is constant. Because t is constant, I can put it inside the derivative here. T ds dt equals du dt plus t s dot j. And move this term to the right hand side and this to the left hand side. And you have minus t s dot gen equals du dt minus t ds dt. But t is constant, isothermal in this case. Because t is constant, I can pull it inside the differential. And now I can combine the two derivatives. And I have that minus ts dot gen equals derivative of u minus ts dt. Okay? And what is u minus ts? A, exactly. And since s dot gen is greater or equal to 0, t is always positive, minus that makes it less or equal to 0. So in this case, what do we have? We have that dA dt must always be moving in the direction of decreasing. The only variations allowed under those conditions are decreasing Helmholtz free. So, and at equilibrium, dA has to be 0. At equilibrium, remember, time derivatives are 0, things are flat. And we can only move in directions of decreasing A. So, at equilibrium, flat, and I can only move in directions of decreasing B. So I can move on this side, this way, and this side, this way. What does that mean? That means the equilibrium has to be minimum Helmholtz free. So the same type of reasoning that we found that under the first set of conditions, entropy must be maximum. Under the second set of conditions, Helmholtz free energy has to be. So A must be a minimum, which means now third set of conditions, case 3. Isothermal, constant pressure. So in this case, the first equation can be rewritten as du dt. Q dot exists, it's not adiabatic. dV dt exists, it's not constant volume. But P is constant. Because P is constant, I can move it inside the derivative. So minus the derivative of PV.